Welcome to the session on stretching the service mesh beyond the clouds. I worked for an organization where we moved from data center to Amazon Web Services. It's a pretty typical story where we had some applications in the data center and we said maybe some of them should be better in Amazon Web Services. And we did a full assessment on which ones went to cloud and which ones didn't. And we were in the process of moving some of them to the cloud when, well, one team came by and said they wanted to use Microsoft Azure instead. This is a valid request, right? There were some important security requirements that Azure fulfilled and Amazon wasn't really sufficiently fulfilling for this team. So we decided to implement a multiple cloud topology. Problematically, we also found out that some of the applications needed to be refactored to use Kubernetes. The original applications that we had moved were using virtual machines, and we found out that some of them might actually be better using Kubernetes specifically, so then we had to build a Kubernetes platform across Azure and Amazon, and then eventually migrate each of these applications to both Kubernetes services in there. On top of that, we found out that some applications would never be able to run in a container and could never be put in Kubernetes and likely would never move out of the data center either. So the result was that we ended up having about 5 different kinds of environments and workloads and topologies, including data center, Amazon, Azure, Kubernetes, and virtual machines. This was rather difficult to manage, and I tried to think of a better way that we could manage it. My name is Rosemary Wong, and I am a developer advocate at HashiCorp. My main goal is to try to find the solutions to some of these problems, like how do you operate a multiple cloud environment and provide one point of control for all of them, right? That's the magic behind technology, is can you offer one point of control across all of these environments that we have? If you're curious to learn more about me or some of the work that I have, feel free to check out the URL I have in this slide, as well as my handle on social media, JOATMON08. All right, so let's think about our main problem we're trying to solve. Our main problem we're trying to solve is that there are multiple platforms and environments. In an organization that's taking advantage of different cloud offerings out there, it's very common to have a couple different clouds as well as infrastructure providers and the data center. It's important from an availability standpoint, but also from a vendoring standpoint. You want to try to get a little bit more variety in there. But more importantly, even if you're using one vendor, you also have multiple runtimes between Kubernetes, serverless, virtual machines, and all of the new offerings that are coming out. So typically when you have multiple environments, you usually control a lot of the communication between the environments with DNS. For example, I might have a DNS like myapplication.mycompany.net, and it spans data center and cloud deployments. So my application in data center is in front of a load balancer specific to data center, and myapplication.cloud is specific to a load balancer in cloud. Then I have one DNS to span it all. Rather than say that I have one DNS to span it all, I might think about putting some kind of infrastructure layer in place. This infrastructure layer in place might have some vanity DNS. So it's a DNS that's myapplication.mycompany.net. But what it's able to do is immediately resolve if it needs to go to data center or cloud. So you can build this infrastructure layer yourself, or you can use a tool that exists to offer this kind of capability. And that provides some kind of initial control over communication between environments. The second piece that you need is some kind of automation to control the infrastructure layer. So in most environments, you'll find that some kind of control plane will exist. And this could be usually in the network, right? So in the case of some kind of software network where you have some control plane that manages and configures that infrastructure layer to funnel traffic between multiple environments. Now, remember, this is important. There's some automation and there's some infrastructure layer. The combination of that is a service mesh. A service mesh is an infrastructure layer that manages and abstracts service-to-service communication. You hear a lot about service mesh in the microservices architecture space. Microservices have a lot of other problems and a lot of other complexities that service mesh offers to solve. That also includes retries, error handling, preventing cascading failures for upstream applications. So there's a lot of ways that service mesh solves problems for microservices, but we can actually apply it to multiple environments and platforms as well. So service mesh provides the automation and the infrastructure layer to handle some of the service-to-service communication between multiple clouds, environments, and platforms. The way this works is that, as I mentioned before, there's two pieces. There's the infrastructure layer in the form of proxies, and there's the automation layer in the form of the control plane. In this case, I'm referring to Consul, but most service meshes use a very similar approach. So Consul uses a control plane. There are the Consul servers. In this case, I have a Consul cluster deployed in the data center and a Consul cluster deployed in cloud. The proxies funnel traffic between them. So anything that has to be service to service goes through the proxies first. For example, the UI application goes through the proxy in order to communicate with my application in the data center. Consul will configure the proxies and therefore control the rules and the placement of where the traffic is allowed to travel and not allowed to travel within the environment. Then we also have the UI to my application. So the UI can also use the proxies to go to my application in the cloud as well. This is important to recognize, especially because this allows the cross-cloud access. So as long as the proxies themselves are able to communicate or are able to provide that level of control, even in Consul, for example, in the data center and the cloud, we're able to control communication across environments as well. So this is why the service mesh provides the somewhat solution to this problem set. But you might look at this and say, hey, Rosemary, if I add a service mesh, doesn't that introduce more problems? And you're not wrong. There is some added complexity, right? You're adding yet another agent to a machine or yet another agent to your deployment. And there are a lot of benchmarks for this now, but it doesn't add that much more. It doesn't add that much more in terms of a performance loss, right? In fact, for the most part, the added layer of abstraction doesn't necessarily add too much of a performance loss or gain one way or the other. However, there is an operational complexity that you're adding. It's more to debug and it's more to operate. The point of failure is now in the service mesh. It's not in the applications themselves. So you have to think about whether or not you want to take on the operational complexity of that. On the other hand, if you don't have a service mesh and you have many environments and you're planning to run them for many years, you often end up having more operational responsibility in the long term anyway. You don't really have any automation, so you have the automation localized to each environment. So, for example, you have localized automation specific to Kubernetes and Amazon versus virtual machines on Azure. You also have multiple sources of truth. You have multiple sources of control, right? You don't necessarily have one view of how an Azure service that's running on Windows is communicating to a Kubernetes service in Amazon running on Linux. There's not really one place that you can control that, and you get that view. On top of that, there are multiple metrics approaches. For every environment that you have a unique metrics solution, and sometimes it helps to work with the vendor solution, and since it's the path of least resistance and it's easiest. The problem is that when you have multiple clouds and you need to aggregate all of the transactions across the clouds, well, you don't really know what kind of standardized metrics you're going to be able to retrieve. So what are some of the solutions to this? We talked a little bit about the problem, which is multiple platforms and multiple clouds, but what are some solutions we can think about in the service mesh space? Well, service mesh has a couple of deployment topologies. So service mesh itself, you don't have to do service mesh across every cloud, right? So the beginning of this talk, I introduced it as stretching the service mesh. We're not going to try to stretch one service mesh across multiple environments. That's a misnomer. So I want to show the different types of topologies that you'll actually have. So imagine this is the topology that you have. You have a data center, you have a cloud, you need to communicate data center and cloud. The first thing you'll do is deploy the service mesh in the cloud, right? So if you have a newer environment, you haven't really done as much to it, it's easier to port in the service mesh if you have a containerized environment in the cloud, it's also much easier to implement the service mesh there. So you start with the service mesh in the newer environment or the containerized environment first. And then you add a network automation piece to synchronize the catalog of the service mesh in the cloud to anything in the older environments. The benefit to this is that in your service mesh, you have the ability to control retries and error handlings to the non-service mesh services. So for example, if I had the UI in the cloud and I needed to communicate to my application in the data center, the UI in the service mesh has the ability to control some of the retry and error handling on the service mesh side. There's also the ability to use progressive delivery techniques within the service mesh itself. So I could do something like canary, A/B testing, or feature flagging. However, in the non-service mesh space, the non-service mesh space still gets the benefit of automated control. So the network automation is still allowing my non-service mesh to be a part of the main service mesh. It gives the illusion of stretching it, even though there is no service mesh at all in the data center. And the added benefit is that I don't have to change existing applications. It's hard to retrofit a service mesh into an older environment, and so I don't have to change anything in the non-service mesh. So today's demo actually implements this kind of topology. I'll use a Consul service mesh in the cloud. So the cloud is using Kubernetes. And I also deploy a Consul ingress gateway. The ingress gateway just helps control traffic from outbound into the Kubernetes cluster. It just makes it easier from a security standpoint. So what happens is that Consul ingress gateway registers a subset of services. It recognizes any updates, as well as any host headers that need to be added, etc. And it will synchronize that information to Consul Terraform Sync. Consul Terraform Sync it serves as the network automation piece. I'll speak a little bit about that in the next slide. Consul Terraform Sync will then configure the application load balancer. So in terms of the topology, we've got a service mesh in the form of Consul and the network automation in the form of Consul Terraform Sync. You can use other tools. This is just one way to demonstrate how the topology and the pattern works. The great part about this implementation is that it is private connectivity between the data center and cloud. However, the downside to this is that you have to have a separate piece of network automation. So I did have to write the implementation to allow the Consul services to synchronize and configure the application load balancer. It's a Terraform module, but you still have to write it. And on top of this, I don't have a way of consolidating metrics. There are still multiple metrics in this environment. So the way the Consul Terraform Sync works is that Consul Terraform Sync checks whether or not the service changed in Consul. It gets the event, and it uses a template to create the Terraform configuration. The Terraform configuration references a module that I've pre-written to configure an application load balancer in Amazon. It runs Terraform, and then it will download the module and apply changes automatically. And the cycle continues. So anytime the service changes, the Consul Terraform Sync agent gets the event and then runs through this template and then Terraform apply cycle constantly. So in this network automation demo, you're welcome to recreate it yourself if you'd like. I did deploy it all in AWS. It is in multiple regions, but it is something that you can recreate. I wanted to make sure it was in one cloud so you had the ability to do a recreation if you wanted. It's deployed in AWS. The data center uses virtual machines in US East 2. Cloud uses Kubernetes in US West 2. So data center, cluster, cloud, cluster. There's also a network automation piece, and that's Consul Terraform Sync, and it configures the application load balancer. So in this demo, we're going to show the network automation topology using Consul Terraform Sync and Consul Service Mesh. So the first thing we'll do is set up the defaults. So by default, what happens in this environment is that the data center gets 100% of traffic. So here we're trying to do, I guess, a canary, but it's more manual in nature. So we ideally want to send a certain percentage of traffic to the cloud. Right now it's at 0. The only time we actually send traffic to the cloud is when the host header is myapplication.mycompany.net. So if the host header is myapplication.mycompany.net, then it will forward everything to data center or Ingress Gateway Cloud. This is actually a new rule on the load balancer that I've created as part of Consul Terraform Sync as sort of the initial load. So this configuration by default will actually go to will go to data center. This is where the default request will go. So if anybody is actually doing this from a user standpoint, what happens is that all the traffic will go to data center by default. I'm using the host header my application mycompany.net as a testing mechanism, so I can actually ensure separately that my cloud application is working before I try to deploy to data center. You'll notice that the logs coming from one of the terminals has some errors, connecting to console. This is Consul Terraform Sync. What it's doing is retrying and connecting to console. Consul Terraform Sync has already run once and applied the rule that is my application, mycompany.net. So that's why you'll see it try to connect just to make sure that it's updated. What it's doing is synchronizing the catalog for the Ingress Gateway in console to this particular application. If I examine the target group for data center, you'll notice that the target group for the data center has one instance. It is a virtual machine that has my application on it. So it is healthy, it's available. Just to show that it is healthy and available, I'll actually make a test to it, and the test will use the host header to the load balancer endpoint. By default, it's sending 100% of traffic to the data center, which is where you're seeing the API response going. This is a handy application that shows where the request is going, and in this case, I've labeled it to go to data center, so it is going to my application in the data center. All right, so now what we're going to try to do is increase some traffic and test whether or not the cloud application is working. So the cloud application is connected to the Ingress Gateway for Consul. I connected it to an Ingress Gateway in Consul just because it controls the traffic going into the cluster and just secures it a little bit more. But in this case, we have 3 instances of my application. The 3 instances of my application connect to the Ingress Gateway. If I look at the tagging and metadata within the instances themselves, the tagging and metadata show that the weight is 0. So this is actually where I control the weight of how much traffic is going to the application load balancer listener rule. So remember, right now it's at 0. When I change that weight in console, that weight will then get reflected in the application load balancer thanks to the network automation from Consul Terraform Sync. So what I'm doing is I'm going into the Kubernetes and changing the service metadata weight. The service metadata weight, right, does correlate to and propagate to console. So that's where that's actually going to be changed. And what Consul Terraform Sync is doing, the network automation piece, is actually reading that weight from the service catalog and then inputting it to a Terraform variable. So you'll see that running. I've added to the application, and it will take some time for the new one to roll out. There's a lot of pods. You'll see a lot of console clients and servers running as well. But you'll notice at the bottom where the logs are scrolling for Consul Terraform Sync that there's a Terraform apply going on. So you'll notice that's the apply complete, resources added. This is because it's being driven by some of the events from Consul. The weight itself hasn't fully changed, right? So it's only going to change when the new application comes up with the new weights. So just to check if whether or not the weights are applied to the new application, you can check tags and metadata and notice that the weights that I changed in Kubernetes have been propagated to Consul and will now be propagated to Consul Terraform Sync. And that's where you see the one changed, right? I've changed the listener rule. There were some modifications done to the load balancer. And now I've done one change. If I refresh the application load balancer listener rules, 50% will go to cloud, 50% goes to data center. And what I can do is test it, right? So let's say I've gone through this process and I want to deliver this application that I've replatformed to cloud, or I've replatformed to a new place, and I'm testing it just to make sure it works. Unfortunately, it does not seem to work at all. And I know that I'm wondering, is this 504 gateway timeout from the cloud or from the data center? And when I examine AWS, notice that it is coming from the cloud. So the cloud is unhealthy, requests are not coming in, there's some problem with it. And so that's why there's a gateway timeout. So I'm able to debug fairly quickly and say, okay, I know that I turned on the service mesh component, I was able to synchronize the network automation. If I actually try to run the command again to the same host, my application, mycompany.net, it will load balance 50% to data center. So I've noticed that there is something indeed not right with my cloud deployment. And in my service mesh, I can debug it. I can go check and see what's going on. But because I've orchestrated this control, right, this mock control using network automation, what I can do is now go back and reset everything. From a user standpoint or a customer standpoint, because I'm setting a host header and isolating it to the host header, I could still say, okay, the top level load balancing or the top level DNS is unaffected. Everything is still going to go to the data center by default. But in this case, I'll reset it back, and Consul Terraform Sync responds by changing the load balancer back to 0% traffic to cloud. So notice this is not using fully a service mesh. It's really heavily depending on the service mesh in cloud being able to synchronize to the network automation for something in data center. So the key, the really nice part about this workflow is that I still get one point of control in some regards. Anytime new services are being registered or updated in my cloud or new cloud environment, I'm able to synchronize them back to an older environment, such as data center or an older cloud. So now that 100% is going back to data center, everything is back to normal, I can resume testing cloud and fixing things. So our next topology is a little bit different. We're not going to use network automation. What we are going to do is stretch the mesh a little bit more accurately. So in this situation, you would deploy a service mesh into cloud, and you deploy a service mesh into the data center. They're two separate service meshes, right? So they're not the same service mesh you're deploying to both. They are two separate clusters of service mesh control. And you set up something called federation between the service meshes. So federation is the idea that there's two separate clusters and they have the ability to control between them. So they have the awareness of what the other is registering from a services standpoint, as well as what it is registering from a services standpoint. The benefits of a federated service mesh is really actually neat because you get one place to control retries and error handling. Both meshes are able to control retries and handling. You can also aggregate and standardize all of the metrics. So recall in the network automation piece, I have separate metrics going in different places. In this case, I have aggregate metrics from all of the proxies, and I can standardize on them. What's also really great about this is that you get the progressive delivery approach across all environments and frameworks. You aren't limited to just the one in the service mesh. So you can do a fully automated canary deployment if you wanted to, and that's what I'll show today. And you can do A/B testing. So, for example, I could set a header to test specifically an application in cloud. I don't have to test the one in data center, and in that case, the A/B test can be done with one single control point in the form of both service meshes. I know it's a little bit hard to picture from a federation standpoint, so we'll actually go into some of the technical details of what federation involves. Basically, what we do is we deploy a service mesh, a Consul service mesh in the cloud, and we label it as the primary service mesh. And we deploy something called a mesh gateway. The mesh gateway allows actually connectivity to other mesh gateways. So the mesh gateways raise their hand and say, hello, other mesh gateway. Here's some of the services I have in Consul in the cloud. Can you join me? And the data center Consul service mesh has its own mesh gateway and says, okay, sure, I'll join. And the two of them are able to communicate with each other and register and identify services in each cluster. So the data center has its own Consul service mesh, and it behaves as the secondary. The reason why I put the cloud as the primary and the data center as the secondary is that if you do this gradual topology where you go from a network automation and you grow into this federated service mesh approach, you're likely to have deployed the primary service mesh in the cloud first. And so you might as well go and add the older environments as secondaries while you keep the, let's say the first one as the primary. Up to you though. The great part about this approach is that you can do it over public or private connectivity. You don't have to have private connectivity to do this. The mesh gateways can communicate over a public network with TLS encryption. However, the downside to this is that you do have to retrofit the service mesh into the data center or an older cloud environment. And it's not always something that people want to do. In this demonstration, I actually am going to show a combination of federation as well as automated canary deployment, which is a progressive delivery technique. The idea behind the progressive delivery technique is that you're able to progressively deliver an application to production and mitigate the risk of, let's say, failure to your users or customers. So in this demonstration, what I'll show is that I have UI and my application. I also have my application in cloud. Imagine that I am replatforming and moving my application to the cloud. So what I'm going to do is I'm going to canary deploy and make sure that my application in cloud is actually correct. The way that this works is that each proxy in the service mesh for both data center and cloud have a set of metrics. The proxies collect request metrics, errors, latency, anything that you can really standardize from a proxy standpoint, it will be able to expose. So the proxies themselves surface these metrics, and Prometheus is able to scrape the proxy endpoints and collect those metrics. Prometheus aggregates the metrics, and Spinnaker can reference Prometheus to do a canary analysis. So Spinnaker is basically a progressive delivery platform that allows you to do an automated canary analysis. It has a component called Cayenta, which will do some statistical analysis on some data points, and based on some metrics that you configure, you can say whether or not the canary should fail or it should succeed. So in this case, Spinnaker will look at one metric. You could be more sophisticated, but I've only configured one metric, and that's errors. So it will check for whether or not the errors in my application have increased in, let's say, the console server cloud deployment. After it's done a canary analysis, it will make the decision on how much traffic to split between data center and cloud. The reason why this is important, especially from a service mesh standpoint and from, let's say, a multiple cloud environment standpoint, is that Spinnaker doesn't really care if it's data center or cloud. What it's able to do is configure console. It's able to configure the control plane of the service mesh and say, all right, 90% should go to the data center and 10% should go to the cloud for my application. The console configuration entry gets propagated to the proxies. So you don't have to worry about going into a load balancer and figuring out how much traffic is going where. You don't have to figure out which service in which load balancer needs to be configured. Instead, what you do is you declaratively configure the service mesh itself to control the traffic management. You can also configure it with headers. You configure it with any layer 7 routing that you need. But for the most part, in this case, I'm going to show the canary deployment and how you're doing this in an automated manner. So as the canary succeeds, we'll increase the traffic, more traffic to cloud over time, and eventually 100% will go to cloud. If you want to check out this demo and recreate it yourself, this is a branch on the repository I showed earlier. It is deployed in AWS. Once again, the data center uses virtual machines. The cloud uses Kubernetes, and Federation sets the cloud cluster as a primary. So there are a lot of windows on the screen for this demo, so I'll explain them first before I move forward with it. The first window on the top left is Grafana. I'm using Grafana just to show the requests and the errors for services, specifically my application, across both cloud and data center. The one on the top right is Spinnaker. Spinnaker is a progressive delivery tool that I'm using to analyze the canary and automatically increase traffic to the cloud application. I also have two windows at the bottom showing two different console data centers. The first is the console cluster for cloud on the left, and then the right has the Consul data center cluster. So there are two different clusters. Notice that it is one user interface. I'll click a drop down and show, but there's one user interface that you can see both Consul clusters. So these are two separate ones, but we are effectively stretching the mesh so that we can do an automated canary deployment. Now, a lot of these techniques that you'll be able to do for headers, etc. But the idea is today I just wanted to show more holistically how you would be able to aggregate and put together all of the metrics from all of the meshes that you're collecting, and then be able to do some workflow from it. So in this case, what we're trying to do is canary deploy cloud from the data center. So the first thing we're going to look at is basically the two separate environments. Right now we have a lot of traffic going to data center. You can imagine this as customer requests going to the data center, my application. There's an upstream UI. So the upstream UI is currently resolving to my application in the data center. So you see me going into the Consul data center and tracing it, and you'll notice that UI goes straight to data center. I can also access the cloud catalog as well from this view. So I can actually use both of them, and that works out pretty well. If I want to go take a look at the actual service and what it's doing, right now the service is going to from UI to my application, and that my application's in the data center. It's reflected in the topology view in Consul as well, so you actually get kind of like an application dependency mapping view in Consul. I'll start a new run of Spinnaker. This new run of Spinnaker will deploy a canary deployment to the cloud instance. You'll notice that Consul updates pretty much instantaneously. Basically, the resolver is 100%, well, now it's going 10% to cloud. And so it's starting the canary. So it deploys about 10% of canary traffic to the cloud instance of my application. The way that this is done in Spinnaker is that I'm using Consul's Kubernetes custom resource definitions. You can configure these directly in Consul. You don't need to use Kubernetes specifically. I used it in the case of Spinnaker because Spinnaker offers Kubernetes integration out of the box. So in this case, I configure a service resolver, and the service resolver just lets Consul know anything that goes to my application cloud goes to data center cloud, which is the, if you'll notice on the bottom left, there's the cloud instance with my application, right? So it goes to the data center cloud and the service my application. Consul will recognize that it needs to redirect anything from for my application cloud to data center cloud service my application. And there's also a service splitter as well. The service splitter is available to control the weight. So originally it starts with 100% to the localized data center, which is data center, and then 0% to cloud. But in the case of Canary, I've got 90% going to the localized data center instance of my application and 10% going to cloud. So these weights increase over time. I had them in increments of 10 to 30 to 50 to 70 to 100. So not perfect increments, but wanting to show the case of Canary deployment specifically. In Spinnaker, you can configure a canary analysis stage. I configure it for 3 minutes, specifically in the Spinnaker pipeline. You can do it for longer, and you should do it for longer. I was doing this for the sake of demo because this demo takes about 20 to 30 minutes to run. The other important thing to recognize is that the configuration also has a field for baseline and canary pair. In Spinnaker, what you have to do is pass certain parameters like location, as well as the name and scope to the metric. And so what I've done is I've just specified a baseline location for data center and a canary location for cloud. So my baseline is located in the data center, my application, and my canary is located in cloud, my application. I also set some pass-fail expectations. So if 90% fails, then we know this canary fails. We'll take a look at the configuration for the canary itself because this is where the service mesh aggregated metrics becomes really useful. In the service mesh aggregated metrics, I'm analyzing one group of metrics from Envoy, and that's errors. So in this case, the Envoy error metrics are being collected by Prometheus and then eventually surfaced to Spinnaker. The Envoy metrics are coming from both data center and cloud. So that's a really great part about this setup is that they're actually the same metrics. There's the same Envoy metrics. They're just aggregated from 2 different environments. And the main metric I'm examining today is the Envoy cluster upstream requests. This Envoy cluster upstream requests basically tracks the number of requests and their response codes. They could be 200s, they could be 500s. The idea is that the metric itself tracks it. It's a counter based on which one the response code is being returned. The other thing that I've done is I've configured a source service. The source service is the name of the service in console, which is my application. I'm checking for the Envoy response code, which is, well, 500s. The response code class is just looking for errors. I could add more sophisticated metrics and groups, but I've chosen just to do one for the sake of this example. And recall I showed the baseline and canary pair in the Spinnaker configuration. That goes into the console source data center. So console source data center is a Prometheus tag. Like I said, it's great to have the aggregated metrics from both service meshes because they're the same, and each of them will have the consistent tag of console source data center. So we'll actually identify which data center it's coming from. So in this case, I can pass location being cloud or data center. And so if the HTTP 500s come from the location canary, which is cloud, Spinnaker identifies that as a problem and is able to flag that. But in this case, I know that this application is successful, and it does take about 20 to 30 minutes to run this. So we'll return when the canary pipeline completes, and I'll show you what happens during a release. But as this progresses, you'll notice that the amount of traffic going to data center decreases in Grafana, and the amount of traffic going to cloud increases, and the number of successful requests are coming back and increasing as well over time. All right, so we're back after about 20 minutes or so, and the canary is about wrapping up. It completed about 100%. You'll notice that in the Grafana graph, you'll notice the number of requests to data center decreasing and the number of successful requests to cloud increasing. They actually meet in the middle. That's the 50% canary. So 50% of traffic had been going to cloud, 50% had been going to data center, and eventually the cloud, the number of successful requests to cloud increase. So as this wraps up, you'll notice that it's progressed through Spinnaker at least has progressed through every stage, and it's completed the release stage. The release stage is wrapping up and cleaning up some stuff in console. So because the console mesh is the one that's offering the control, we need to be able to clean up and set the default to cloud. So what I've done is I've set the resolver. By default, anything that's my application goes to the data center cloud, service my application. This is something you'll actually notice in the console topology on the bottom right. You'll notice that the resolver now directly goes to cloud. Nothing goes to the data center. So even in the data center view, for console in the cluster itself, I'm able to view the application dependency in a way that shows me very clearly that it's going to cloud. If I refresh my service will now go to from UI data center to my application cloud, and it's able to resolve that. So regardless of the runtime, regardless of the environment, the region, etc., I pretty much get one view, and I'm able to do some techniques in progressive delivery, basically, using these aggregated metrics across the service meshes. So I showed a successful canary deployment using the service mesh and the aggregated metrics in Spinnaker. But what happens in the case of a failing one? Remember, in the network automation demo I showed, I manually increased some traffic to the cloud instance, and it actually didn't work. So I reverted back to 0% traffic to the cloud and 100% to data center. What I've done here is I've started a pipeline that starts a canary deployment, but the application itself has a small error rate. And in this case, we're proceeding with the same workflow, right? The same technique, which is let's do a canary deployment, send a certain percentage of traffic using the console service splitter, send a certain percentage of traffic, use Spinnaker to collect the metrics and evaluate if there are HTTP 500 errors, and then ultimately respond to the case. So here what I'm showing is that this is fully automated. In the network automation case, I was doing this manually. I was looking at the metrics across 2 different places and sort of hand waving whether or not it was working. In this case, I'm actually allowing Spinnaker and by extension Kayenta to analyze what the metrics are looking like. So if you examine Grafana, the metrics are showing that there's some HTTP 500 errors for cloud. There's a small number of successful requests that are going through for cloud, and the error rate is pretty small, but it is introducing some errors, and that metric is increasing. The canary analysis in Spinnaker is going to recognize that and flag it as a problem. Right now, there's only 10% of traffic going to cloud. In this scenario, we again use the same workflow, and it's just demonstrating a failing application. The main difference is that when the canary fails, what Spinnaker will do is execute a rollback canary. This is something I've created, but the rollback canary just sets all of the traffic back to the data center application. The reason why I set all of the traffic back to the data center application, it's similar to the other scenario that I showed in network automation. By sending 100% of traffic back, I'm able to ensure that none of the customers who are using my application are affected. 100% is still good. They're able to use it, but I can debug the application on the cloud separately and identify what is causing the error. All right, so in summary, there's 2 different kinds of topologies you can approach when you're stretching the mesh, right? The first is doing some kind of network infrastructure automation. The benefit to it is that you use what already exists and you add a layer of automation to it. It's a nice middle ground or a stepping stone for full service mesh federation across all environments. The idea is that you can abstract the environment, application framework, and runtime when you're able to federate across multiple service meshes in multiple environments. It also adds an additional layer of control that aggregates and standardizes network policy, metrics, and service-to-service communication in one view. So you don't have to go back and debug multiple systems and track through transactions across multiple environments. The idea is that you have one place to control all of that. Now, it's very difficult to do, right? It's not that this is the end solution for everything, and at the end of the day, you can choose to either stay with some kind of network automation topology and continue that for a couple of years, or you can invest time into making the federation topology work. Either way, there are some options in which you can actually use to manage service-to-service communication across multiple platforms, clouds, and it's agnostic to the environment, application, framework, or runtime. If you're curious to learn more, I've aggregated the list of references here. There's additional information on how to configure Spinnaker with Consul to do automated canary deployment. There's also some tutorials as well for the network automation that I've shown today, like Consul Terraform Sync, as well as some documentation on service mesh itself. If you would like these slides, you can find them at joatmon08.github.io. Thank you, and I appreciate you tuning into this session today.